So another application of our first order differential equations is to simple electrical circuits. Kirchhoff's law eventually relates the relationship between voltage, current, and amperes at a specific time t, such that the resistance di dt plus, the inductance di dt plus the resistance I plus is equal to E of t, where E of t is the voltage, R is resistance, and L is inductance. And for those of you that have never seen a simple electrical circuit before, let me diagnose what all of those things are. So we have a very simplistic circuit, and here's the different components. R is the resistor, and what a resistor does is it basically limits the amount of flow that's going through there. So if there's going to be an impulse that's going to be extremely high, what the resistor does is it kind of moderates that, so it tones it down a little bit, so that way when it goes through, it's you only get the necessary energy, not every single thing that you need, not the complete impulse. This inductor L is usually a coil or sometimes a choke, which basically is going to store the energy in electric circuits. In sound waves, if you're going through audio waves, then what it'll do is it'll reduce some of those high frequency pitches. All right, so if you're building a TV or a radio or something like that, you probably want to have some of these inductors in there to get rid of some of those really high frequencies. And then out here, this is the charge that comes out of it. This is basically what the usable energy is. All right, so that's the essential composition of one of these basic electrical circuits. The voltage is obviously measured in voltage, that's E of t. And in the problem we're going to look at, it's going to be a constant voltage, which most batteries are constant voltage until they end up dying, or something goes wrong, like the coil breaks or the resistor decides it's going to go. Resistance, measured in ohms, is going to be how we're going to limit the flow through that circuit. Inductance, stores, okay, measured in henries. And then the current is basically going to be the rate of change of the electrical charge. So how quickly is that charge moving? Usually electrical charge is very, very quick to get up to its maximum. All right? But initially the rate of change climbs within maybe the first second or two. It's similar to when you turn on a light bulb. It's eventually the light bulb has a constant sort of luminous which it gives out. But it takes a little bit of time sometimes for bigger lights to kind of warm up. All right, so like if you've ever been to a baseball game at night, they turn on the lights. It takes a while for those lights to get up to full power. All right, so this rate of change is slower in larger light bulbs, and it's the same thing with other sorts of current. So let's take a look at a very simplistic problem. A simple circuit has a resistance of 12 ohms and inductance of 4 henries. And the battery has a constant voltage of 60 volts. The switch is closed when t equals 0. So we want to find the function to measure the current, and then we're going to find the current after 1 second. Now, let's remember that our differential is going to be L di dt plus R I is going to be equal to E of t. And if we substitute, we know that R is going to be 12, L is going to be 4, and then E of t is going to be 60. I of t is what we're finding, and we're saying that at 0 seconds the switch is closed, which means that there is no current going through that. Right? If the switch is closed, it means it's off. All right, which means that there can't be any electricity going through it. If there's no electricity, there's no rate of change of that electricity. And what we're looking for is I of, or I'm sorry, this is I of 0 is 0, not t of 0. So this should be I. So sorry about that. And I at 1 is equal to what? That is ultimately the question that we're trying to answer. So now we're just going to substitute. We have 4 di dt plus 12I is going to be equal to E of t, which is 60. We can divide by 4 to isolate di dt. So di dt plus 12 divided by 4 is 3i, 60 divided by 4 is 15. And at this point, it's either a separable or a linear differential. Since we did two separables, let's just do a linear one, and this should be pretty easy. We know that our p of x is the coefficient of I, which is 3. Q of x is 15. And our integration factor, I'm going to define that as IF. Usually we call it I, but we're already having I, so I can just call it IF, is going to be e to the integral of 3 dt, or in other words, that's e to the 3t. And if you recall our formula for solving a linear differential, which we've done multiple times, I is going to be equal to 1 over the integration factor, so 1 over 3t, integral of q of x, which is 15, times integration factor, e to the 3t, plus c. Very basic. There should be a dt in here. Sorry about that. Very basic integral to evaluate. We're going to divide by 3 because we have a linear term. It's the reverse of the chain rule. So I, or I of t, is going to be 1 over e to the 3t times 15 divided by 3 is 5e to the 3t. So antiderivative of e is e, and then we divide by that 3, plus the constant of integration c. All right, and we know at 0, the time is 0, we can distribute through. All right, so if we distribute through, we end up with 5 plus c over e to the 3t, and that's our general solution. The particular solution says that at 0, so 0 equals 5 plus c over e to the 3 times 0. E to the 3 times 0 is 1, so negative 5 is equal to c. And so our function I of t is actually a pretty easy one. So I of t is going to be equal to 5 minus 5 over e to the 3t. And of course, ultimately what we need is we need I at 1. So I at 1 is going to be equal to 5 minus 5 over e to the 3rd times 1. And let me compute that really quickly. It's probably going to be really close to 5. Um, 4.75, and that's going to be in amps. All right. So hopefully that gives you a very basic overview as to being able to solve one of these types of differential equations that require use of Kirchhoff's law to apply this. So in the next video, we're going to take a look at being able to solve a differential with respect to inflow and outflow mixing types of problems.